Hello everyone, my name is Jason Gregerson and this video is going to be Introduction to Linear Transformations. Now our goal in this video is specifically to define and then identify linear transformations as opposed to just transformations. After that we're going to observe some special transformations. So let's get started. We'll start off right away with our definition of a linear transformation. A transformation or mapping is linear if these two conditions hold. So we're given some vectors u and v, and this says that if we take the transformation of the sum of the two vectors, that's the same thing as taking the sum of the transformations of the individual vectors. That's the first property. And the second property says that the transformation of some constant c, there's my constant c, times a vector is the same thing as the constant times the transformation of the vector. So my transformation is linear if these two properties always hold. So to combine these two properties, we could also write that t of c times some vector plus v times some vector is the same thing as c times t of u plus t of v. So what does it look like for a transformation to satisfy these two things? We'll start off with an example. We're going to let t be the transformation that takes some x and it maps this to f of x, where that function value is going to be defined to be 2x. So we're going to think of this function essentially as a transformation. It takes x as an input, where x is some real number, and it maps it to 2x. And of course, if we plotted this function, we would see that it's a line through the origin. And so we kind of expect it to be linear. But now let's use our properties to actually show that this is a linear transformation. Well, we have to show the first thing, that f of x plus y, so I have two values I'm putting in here, somehow this needs to be equal to f of x plus f of y. Now if I can show that's always true, then I've satisfied that first property. Well, by definition, f of x plus y is just 2 times the quantity x plus y. I'm just changing the argument from x to x plus y. So everywhere I see an x in the definition, up here, I'm going to replace it with x plus y. But of course, these are just real numbers in this case. So now if I distribute that 2, I will get 2x plus 2y. But 2x by definition is just f of x. And 2y by definition is just f of y. Therefore, this is equal to f of x plus f of y. So I've shown that first property is true. F of x plus y is equal to f of x plus f of y. Now I need the second property. I'm going to start with f of c times x, where c is some constant. By definition, this is 2 times the quantity c times x, so I've plugged in cx where the x was. Now once again, just using my properties of real numbers in multiplication, I can rewrite this as a c times 2x, because I know that multiplication is associative and commutative in the real numbers. But this is just c times f of x. And so I've shown that f of c times x is equal to c times f of x. So this is kind of a basic demonstration of how I would show that a transformation, or in this case a function, is really linear. So now what I'd like you to do is try some problems on your own. So now let's take a look at some different examples. Here I have 3 examples. The first one is multiplication by a matrix. The second one is integration over some interval. And the last one is a standard looking function. And so let's talk about whether these different transformations are linear. So we've seen in an earlier video how I can think of multiplication by the matrix A as a transformation. So my transformation is defined by taking some x vector and mapping it to A times x. Another way to define that transformation is t of x is equal to A times x. So that's my transformation. Now, is this transformation linear? Well, once again, I have to show that the first thing is true. I have to show that t of maybe some vector x plus some vector y, these are vectors now. Well, by definition, that's just A times the quantity x vector plus y vector. And now once again, because I know my properties of matrix vector multiplication, I know that this is just A times x vector plus A times y vector. But this is just the definition of t of x plus t of y. So when we talked about matrix vector multiplication, we were given this specific property. And now we can kind of see why we were given that property. It helps us show that matrix multiplication is really a linear transformation. At least it starts to. Of course, we have to show the other property is true as well. Well, we'll start with the transformation of some constant times x. By definition, that's a times the quantity c times the vector x. But once again, if we just use our basic matrix vector multiplication properties, this is the same thing as c times a times the x vector, which is a c times t of x. So now because I have both of these properties, I can see that the transformation represented by matrix multiplication really is linear. Let's look at the second one. Now the second one might look very strange, especially if you haven't had calculus too. So this is an integral. So I'm taking the transformation as acting on some function x, and maybe I didn't specify that's some function of x. What my transformation is doing is it's mapping my function value to the number that is the definite integral from a to b of this function, of integrating this function. So this transformation, is it linear? I just have to show, once again, that t of, in this case, my argument are going to be functions. So t of f of x plus g of x, is that really equal to t of f of x plus t of g of x? And we can just check this thing out. So by definition, t of f of x plus g of x is equal to the integral from a to b of f of x plus g of x. But I have properties of integration. I know that the integral of a sum is the sum of the integrals. So this is really just the integral from a to b, f of x dx, plus the integral of g of x dx. And then by definition, this is t of f plus t of g. So I've shown that first property is true. And really the process is the same for the second property. If I look at t of c times f, that's just the integral from a to b of c times the function, integral of the function. But I know I have a property that I can pull that constant outside of the integral. So this is c times the integral, which is just c times the transformation. So that's my second property. So once again, this transformation, which is representing an integral, is also a linear transformation. Now let's look at the last one. Well, this last one should be a piece of cake. We have this function, f of x equals 2x plus 3, and if I were to plot this function, it would be a line. So I definitely expect it to be linear. But now let's go through the process. Let's show that these two properties hold. If I look at the first property, t of x plus y, well, by definition, that would be f of x plus y, because my transformation is representing this function. And so this should be 2 times the quantity x plus y plus 3, which is equal to 2x plus 2y plus 3. Now this piece right here, this 2y plus 3, that would represent f of y. So now I'm left with 2x plus f of y, or 2x plus t of y. But this leftover value, this 2x, is not f of x. I'm missing that value of 3. So this does not satisfy this first property. And thus this line is not a linear transformation. That certainly sounds strange. But when we think about functions, linear functions, they're a little bit different than when we talk about transformations and linear transformations. It turns out that lines that go through the origin, if we let our transformations represent those functions, those are linear transformations, but not lines that don't pass through the origin. So that's what we've learned today, that a line apparently is not necessarily linear. All right, now what's the point of these different examples? One of the big ideas is that we can express linear transformations using matrix multiplication. We saw that in the first case, that matrix multiplication was a linear transformation. But then we saw other things that we could also represent as linear transformations. And so we can really represent these things using our matrix multiplication, using our concepts of linear algebra. So this is the building blocks of extending our theory, our concept, to things that aren't just matrices and vectors. The last thing we'll talk about is maybe the graphical representation of some of these transformations. So first I'm going to do some basic matrix multiplication. I have 3 examples here. If I multiply this first one out, if I do the row vector multiplication, in the first position, I get 1/2 plus 0. And the second position, I'll get 1/2 times 2, which is 1. So this would be my result. If I multiply the second one out, I will get the result 1, 2. And if I multiply the last one out, I will get the vector 2, 4. This is just doing the matrix multiplication. But then when I take a closer look, if I'm thinking about this as a transformation, if I have my equation ax equals b, and I'm really thinking about that in terms of a transformation that's taking some vector x and outputting a of x, which is equal to b here, this right-hand side, I say, what's really happening to my vector x? Where is it being mapped to? In the first case, 1, 2 is getting mapped to 1/2, 1, which really just looks like, 1/2 of my x vector. In the second case, I just have 1 times my x vector, or just x. In the last case, it looks like this is just 2 times my x vector. Of course, I can see where this 1/2 comes from. It's the values on that diagonal right here. And I can see where this 2 comes from. And so this is going to lead me to try to generalize this result. If I take some matrix that looks like R0, 0, R, and I multiply it by some vector, x1, x2, the result is just going to be R times x1, R times x2, which is just R times that vector x1, x2. So it's just R times the vector x. That's what this transformation is really doing. And so if I think about, once again, transformation terms, t of the vector x is just transforming it to R times x. And this is a special transformation. It's just stretching or shrinking our vector. To summarize the result, I have if t of x is a transformation, represented by this matrix, then if the absolute value of r is less than 1, then t is a contraction. So if r is smaller, I'm shrinking my vector towards the origin if I'm plotting this as a position vector. If the magnitude of r is greater than 1, if I'm multiplying it by 2, for instance, then I'm stretching that vector away from the origin if I'm thinking of this as drawn as a position vector. So I can see that matrix multiplication, I can really think about it as transforming a physical vector on R2. And in a later assignment, we're going to look at Mathematica and see if we can plot these vectors and do some different transformations. All right, this concludes this video on linear transformations.